Good. Okay. Good morning. So first, I brought some extra hard drives, and there are more. Even if you blow these ones up, it's fine. So I put them inside here. Now, secondly, I'm getting a bit concerned that the voltages you need to do the test to demagnetize, to find the demagnetization limit, can run into some higher voltages. It's because some students send me emails and ask me, that actually it's pretty hard. Some of these drives are very good magnets. Not all the drives are the same that I gave you, but some of these drives are high performance drives. They have very strong magnets. It's very hard to demagnetize. So if you try, say, up to 5 or 10 times operating current, and it's still not demagnetized, just put a note in the report that it's at least 5 times or at least 10 times the maximum steady state operating current. Because in some of these drives you may end up getting up to dangerous voltages if you really want to demagnetize it. So I'm a bit worried about safety. So basically, as long as you try it, if you didn't manage to demagnetize at a voltage, say, of 100 volt, just say in the report it's still magnetized, and don't try any harder. Okay? I mean, I don't know how familiar you are with safety and working with power, because I got really worried when none of you understood how the grounding works in a house. so that's why. Okay, good. Okay, so to recap what we talked about on Tuesday, the last thing we talked about is microstepping. So just to recap it, first I explained that in a synchronous motor or in a rotating field motor, these two terms are a bit synonymous, because all rotating field motors which have a permanent magnet in the armature, the permanent magnet is running synchronously with the rotating field. So not all rotating field motors are synchronous, but all synchronous motors are rotating field. Right? Synchronous just means that there is no slip. There is a magnet which follows exactly the rotating field. So we said, first of all, that in synchronous motors, if you have one pole pair, or what in some books it's called two poles. As I said, there is some confusion about the terminology, because magnets always come as pairs, in north and south. So in some books it's called one pole pair, and in other books the same thing may be called two poles. In some books, when they say two poles, they actually mean two pole pairs. So you have to be careful with the names. So the synchronous speed at 60 Hertz will be 3600 RPM. And what that means basically is one rotation per sine wave. Okay? And then you can have 2 pole pairs, 4 pole pairs, and it's just this number divided by 2 by 4 and so on. And the example we gave is a stepper motor, which is probably the most common motor you are familiar with in control systems. And how many pole pairs does a typical 200 steps per rotation motor have? 50. And you understood all that, right? And I gave you a demo how it runs at this speed divided by 50 when I plug it in with a capacitor to the power line. Good. Now, so that stepper motor is a 2-phase motor, not a 3-phase motor, simply because you're not so concerned about efficiency of transmission power. You're more concerned to make it simple. So we have a sine and a cosine. Okay, and so instead of driving it just with a square wave, which is one way of driving it, you can also drive it with a synthesized sine and cosine. And the advantage of driving it with a synthesized sine and cosine, that instead of having 200 discrete steps per revolution, you can have as many steps as you want. Because each time the sine and the cosine advance a little bit, the rotor will keep turning, because advancing along the sine and cosine means the rotating field vector is rotating. So at this point, the rotating field vector, let's say, is here, If I go to here, the rotating field vector is here, but if I go anywhere here, the rotating field vector continuously rotates as I follow the sine and cosine. So by putting small enough steps, okay, I can make it go very, very slowly and precisely with no steps, with no jumps, and I can freeze it at any point. So if this keeps on going like this, I can freeze it and hold position and then continue. Okay, that's very nice. And I explain an important thing, that freezing the sine and cosine at a moment in time is not the same as disconnecting the drive from the motor. Because superficially, when you look at a stepper, when you disconnect the drive, it seems to hold position as well. When you just look at it, you unplug it, it seems to stay in the same position. However, there is a big difference between disconnecting the drive and freezing the sine and cosine at given values, and the difference is because the motor internally has 50 positions where it likes to be, because after all it's a magnet with, even if the magnet looks smooth, it actually has 50 poles, and the field has these slots. So the natural tendency of the magnet is to align where the shortest air gap is. So if you stop the power at this position, the magnet will turn a little bit, because these things want to align with a salient pole, poles which protrude. So it will, without power, a 200 pulse per rotation stepper without power will snap into one of 50 positions. But with power, by freezing the sine wave, it stays exactly where you want it to stay. Okay, yes please.
If after you freeze it, you switch direction, does it drive the other way?
Yes, okay, so that's a good question. Let's talk about directions in general. First of all, you can go back and forth in the sine wave, because the same way I went up to here and the vector rotated to here, if I go back in the sine wave, the vector will rotate back, because the relative value of the sine and cosine uniquely defines a position in a 330-degree circle. Because with, say, beginning is this, now at some point the cosine become negatives and the sine become negative, so it basically defines the position of the vector in the full 4 quadrants. So if I want to reverse position, I can go backwards in the sine or cosine. In other words, what it really means, I can switch and make, instead of making one leading, I make one lagging if I go backwards. It's the same thing. Physically what it means, if I have a fixed sine and cosine and I want to switch the direction of the motor, what I do is I take one of the coils and reverse them. Because reversing a coil is like inverting the polarity of one of those. And if you invert the polarity of one of those, it seems that I switch the order of the phases. One is leading instead of lagging. Okay? It's the same thing of this definition of sine and cosine. If I have here sine and cosine, I have this vector rotating this way, but if I reverse this axis, okay, the vector will rotate the other way in the classic way I construct the vector by adding these two together. So in all synchronous motors, if I have the field rotating one way, the armature will go one way. If I two-phase motor, if I switch connections of one coil, it's the same as switching the order, which is leading, which is lagging. Motor will go backwards. Okay? Now in a three-phase motor, if I have a three-phase motor like this, with the 3 coils, and I want to switch direction, what do I do? So if it's electronically, say if I have the sine waves generated electronically, I can go backwards in the sine wave. But let's say it's connected to a power line, and it goes this way, and I want the motor to go this way. What do I do? And how do I do that physically? Correct, but how do I do that?
Switch 2 of the wires.
Switch 2 of the wires, because think of it. Let's say this reaches peak first, and then this reaches peak, and this reaches peak, so the direction is this way. If I switch 2 wires, so this coil will be here, so this will reach peaks, and this will reach peak, and then this will reach peak, so the field will be rotating the other way. Right? The easy way to visualize it, just look at the peak. So because you have 3 sine waves, now think of it in which order they reach maximum. So if the order is A, B, C, that they reach maximum, and I switch to wires, B will be here. So it will go A, B, C, go in the other direction. Okay, so if you have a 3-phase motor and it goes the wrong direction, you just switch to wires. Okay, if you have a stepper motor, goes the wrong direction, you switch. In the stepper motor, the 2 coils are actually separate. So if it goes the wrong direction, just switch 1 coil. It's the same, you switch to wires. Now if the stepper motor is already connected like this, as a 3-wire connection, then it's a problem. Then you have to disconnect the coil and switch. At the end of the chapter on motors, I'm going to summarize all the motors, and then I'll go over how you switch directions in all types of motors. But in generally, it's if you switch a coil, everything switches directions. Okay, so that's microstepping. So now let's talk a little bit in general about the characteristics of synchronous rotating field motors, and particularly stepper motors. So before, when I talked about the motor, I made a diagram. This was omega, and this was torque. And as you recall, PMDC looked like a slanting line, say. So this was PMDC. Series wound DC had some very desirable characteristics. So this was universal or series DC. Now, what in this graph, what would a synchronous or a rotating field motor with a permanent magnet armature, what would it look like? So I connect it I connect it, say, to the power line, make it rotate at a certain frequency. How does that speed change with load? Think of this example of the stepper motor with the capacitor to split the phase. I connected it to the power line, it rotated at 72 RPM, but I want to make a plot. How will that speed change with torque? Flat. Exactly, because synchronous means it cannot change speed. It's locked to the frequency of the input, it cannot change speed. So it will be flat, completely flat, fixed by omega. So this will be, say, omega 1, omega 2. If I want to change the speed, I cannot change it with load or voltage. All that I have is change the frequency. Up to a certain torque, and what happens at a certain torque? It crashes, because at this, what happens, let's draw it a little bit. If I have a rotating field vector like this, and it's pulling after it the magnet, this is NS. Now the field is rotating and it drags the magnet after it. Now what happens when I start loading the magnet? If there is no load on the magnet will exactly align with the field and just follow it. Just like in the demo with the compass I gave you, okay? Now, if there is a load on the magnet or on the shaft of the motor, the magnetic field is not a rigid coupling. It's more like a spring. If you put a torque on it, it will drag it as if it was connected by a spring, because a magnet is not like a gear. It's not positively linked. It's just a force which behaves as if there was a spring. So what this behaves like, I'll draw it a bit bigger here. What it behaves like, if this is a rotating field and this is the armature, and I start loading the armature, it behaves as if there was a spring here which is pulling the magnet after the rotating field. That's a spring, not a coil, right? Let's say call it K, so you remember it's a spring. So as you increase the load, this spring winds up, okay? And there is an angle formed between the axis of the rotating field and the axis of the armature. This angle in motors, it's called power angle. Okay? And to visualize it, imagine that if this was a magnet and I try to drag a piece of steel after me, okay? So I'm dragging this piece of steel. If the friction becomes bigger, somehow it will open up the gap more. That's not such a good example, because here when it opens up the gap, the force will go down. But still you can see that the coupling is elastic between this, and as you load it more and more, okay, this angle will open up till a certain point where it becomes unstable, because when this angle becomes 90 degrees, okay, it becomes unstable, because at some point, if this angle becomes 90 degrees, the force will actually start going down, because this thing is so far away, it's lagging so far away that the force starts going down, and at some point it'll actually want to snap back. Okay? If you think of the example, think of just magnets. Think of, you take an armature NS, and you take a ring, and you mount on it two magnets. Forget it's a motor, just take two magnets, mount it on a ring, and you start rotating the ring. When you rotate the ring, this thing will follow with no load. As you start putting more and more load on this, what will happen? The ring will be here, but this will fall behind. Now at some position, say when the ring is here, and the magnet falls behind so much that the power angle is 90 degrees, there will be very, very little torque. Okay? Because you can imagine if that ring goes a bit more, actually it will repel. Instead of pulling it, it will repel it. So you can see from this example that it behaves in a strange way. At the beginning, the spring appears weak because a little bit of rotation doesn't create much torque. Then as you go up here, if you increase the rotation, this imaginary spring tensions up, okay, and it gives more torque. But at some position, say for sure, if this was 180 degrees rotated, S will be S and it will repel, there will be no torque. Okay, so if you analyze it, you see that what happens if you draw a graph, this is theta, the power angle, and this is the transmitted torque. At zero power angle, there is very little transmitted torque, because it can move a little bit and it doesn't generate torque. Okay, the torque goes up to 90 degrees, and then the torque actually starts going down again, and it turns out that's a sine wave. It's a sinusoidal curve if you analyze it. So that power angle can only reach 90 degrees, and after that there's no torque. So as you load the motor, what happens inside, it starts winding up and the power angle increases, but it's still synchronous, it still follows. But at some point it becomes unstable and collapses, and actually, strictly speaking, it doesn't even collapse like this, because once it starts collapsing, it's actually collapsed backwards to zero torque. Okay? But for simplicity's sake, let's say it collapses like this. Now, the reason why that's important is that also underlines the only problem a synchronous motor has. And the problem is starting torque. Because when you start that motor, if you apply the full frequency, the rotating field spins at full speed, while the magnet didn't have a chance to lock in yet. So imagine what happens if the magnet is stationary, and we take this imaginary ring, which has two magnets on it, which represents the rotating field. So we have this imaginary ring, and it has two magnets, and we spin it, that's a rotating field. So if we start slow, it will drag this with it. Everything will be fine. But if this starts spinning at full speed, like we plugged into the outlet, now this, at the beginning, it starts pulling this way, but within a fraction of a second, this S already appears on this side, because this still didn't have a chance to move. That already made a full turn. This S will appear here, and it will pull this backwards. Okay? So if everything is slow, this will follow. But if things are so fast that this didn't have a chance to move much before this S did the full turn, it will just sit and vibrate. Maybe there will be a small net torque, but in general it will vibrate until it manages to lock in. So this is a typical problem of synchronous motors, that if they have a big load, especially big inertial load, say big flywheel, this cannot lock in because the field goes so fast that it just vibrates. And exactly the same happens with a stepper motor. As you probably know from your labs that you played with stepper motors, if you want to get a stepper motor to go fast, you have to what's called ramp it. You have to give it a frequency which goes faster and faster and faster. If you apply the full frequency immediately to the stepper motor, it will just hum. It wouldn't lock in. Or the other experience is if you have a servo with a stepper motor which is running fast and you stall it, you put your hand on it and stall it, then when you take your hand off, it doesn't resume speed, it just vibrates. Now how many of you had this experience? How many of you know what I'm talking about? Okay, so I see that some of you played with it. Good. So the reason why so when you drive a stepper motor, you want to get it to go fast, you start slow and you ramp it. You go faster and faster and faster, and when you want to slow down, you have to ramp it backwards. Okay, if you want to maintain position. But if you stalled it here and restarted it, it wouldn't be able to snap in because the inertia doesn't allow it to snap in. So this problem is typical not just of steppers but of all synchronous motors, and that's their weakness. They have very poor starting characteristics. Now compare it to the DC motor we talked about. The DC motor we talked about is the opposite. At start it has the biggest torque and it pulls in and accelerates both types, PMDC and series, especially series. At start there is no back EMF. The current is the biggest, the torque is the biggest. So it can start with a huge load and you don't have to worry about it not starting. It will just slowly accelerate the huge load until it speeds it up. Okay? So if you think of a starter in a car, every car has an electric motor to start the engine. Which motor would you put in a car starter? A synchronous motor or a DC motor? Obviously, because the little motor has to drive the whole car engine. Synchronous motor doesn't have a chance as a starter. Okay? Now, it's a more subtle question. Which DC motor would you put in a car starter? A PMDC or a series wound? That's a more subtle question. Which one? Most likely, yeah. So, because a PMDC, there is one problem with PMDC, that it has a finite magnetic field. So if you want huge torques, it cannot give you more torque than the strength of the magnet, because the torque is a product of BLI, and the I tries to demagnetize the magnets, just like on your hard drive you're trying to demagnetize the magnets. So if you have a huge current, it can even demagnetize the magnets. Okay, or at least once it reaches the reverse field, which equals the magnetic field, it cannot generate torque anymore, because the coil itself generates a reverse field. Right? The torque of the motor is the interaction between two fields, the permanent magnet and the field created by the armature. But if you drive 1,000 amps into the armature, it creates such a big field it overpowers the field. Okay, but in a PMDC, in a series DC, there is no magnet. So just one coil around the stator and one coil in the rotor, and there's nothing to demagnetize. And because there is an air gap, there is less chance to saturate the magnetic material. So the more current you drive, the stronger the magnetic field becomes, both of the armature and of the stator. But there is a danger in that. And the danger in that, as you recall, when the load goes down, the speed goes to infinity. Okay, so it's dangerous, and I'm not sure what they do in modern cars, but sometimes you want to add, as I discussed, a second winding just to limit that speed when the load removes. Actually, you can hear it in a car, because in a car, sometimes when the car didn't start, you can hear the starter disengage and make a high-pitched whine. Because the car is designed that the starter motor disengages as soon as the car started. But sometimes it disengages before the car started, so you can hear it cranking the car, and then you can hear it making a huge whine when it disengaged, and suddenly the torque went to zero, so the speed went to thousands of RPMs. Because you can hear it do crank, 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 and then whee when it is engaged. I don't know if you notice these sounds, but if you listen, you can hear what the motor is doing. Okay, so this motor would have been the best in the world because it's constant speed, very easy to control. You can control position, not just speed. In a DC motor, you can only control speed, not position. You have to feed back the position through an encoder in a servo. In a synchronous motor, you actually are controlling position, not just speed. That's very good. That's why you can run stepper motors open loop. You tell it go 50 pulses, it goes 50 pulses, right? So it's a very good motor. The only disadvantage is starting torque. Now, in microstepping, it's a little bit misleading because it gives you the appearance that you can really have infinite resolution. So if you have 200 steps, it's 1.8 degree per step. But if you microstep, especially if you look at the spec of the microstepper, it says 10,000 pulses, 20,000 pulses per revolution. It gives you the feeling that you have infinite resolution, so you don't need any kind of feedback at all. But in reality, when you microstep, there is a limit to the resolution you can position things. Can somebody think why is there a limit? Why can't you position a microstepper, say, to a thousandth of a degree?
Because the way that the sine and cosine waves are actually made is not, it is discrete.
No, because you can have a 12-bit counter, and you can have a very high resolution counter and a very high resolution lookup table. So you can have 16 bits. It's very cheap to add bits. So that's actually maybe one limit, but it's easy to overcome. But there is if you build a stepper motor and measure the angle very accurately, especially with a load on it, and you give it these little micro steps, which are equivalent, say, to a thousandth of a degree each, and you measure the armature position, this makes quite a big error compared to the commanded position. Quite big, I mean a tenth of a degree, a hundredth of a degree. So why is that? Why can't you actually control a stepper to infinite resolution if you have a perfect sine wave? Yes?
Friction, static friction to overcome the first.
So why can't this rotating field position it exactly? There is friction. True, friction is one part, there is load, there is friction, but you tell it go to a certain angle. Why can't it go to that certain angle?
The windings aren't exactly the same.
No, not quite. That's also true, but that's not the main reason.
I was going to say kind of the same thing. It's non-linear.
No, it turns out the answer is much simpler, okay? If you could control the motor exactly, it means that spring inside would have to be infinitely stiff, because a magnet follows the field as if it was tied with a spring. Now, if the motor is positioned somewhere and you say go to the next step, okay, the next step is just one microstep away. You go from here to here, so the currents in the motor change maybe 0.1%. Okay? Now, this 0.1% change in current, which could be approaching zero change in current, at least has to overcome static friction and also the load and everything. So you would need a very good spring that if you pull this just a teeny bit, this will follow. But in reality, that spring has some finite stiffness. The stiffness is given by that graph. Remember this graph, let's say you're sitting here, especially here at the beginning, you have you have quite a weak spring. You have quite a small torque. So another way of looking at it, at the best, this spring has some ratio between torque and theta. Okay? So if you generate a very small delta theta, you are generating a very small delta torque. So I'll redraw this to make it clear. I'll redraw it here. So we said that if we make a graph of torque versus theta, where theta is power angle. Power angle is this angle between the field and the actual position. And the graph looks like this, and after this it actually continues like this, but we don't care. Now, if you change the phase between the rotating field and the armature by a tiny amount, by delta theta, so this is delta theta, you only can generate a very, very small change in the torque, which is delta torque, which is, if this goes to 0, this goes to 0. So a small change in the angle will generate a tiny change in the torque, which may not be enough to move anything. So in other words, the motor is a bit soft. Okay, it's spring coupled. Now, if you have a motor driving a load with a gear, okay, if you move the input of the gear delta theta, the output of the gear will move delta theta divided by n. N is the ratio of the gear, but it will be stiff. If you move it another thousandth of a degree, it will move another millionth of a degree, because everything is stiff. It's not springy, it's rigid. Okay, but if you have something connected with a spring, you can move a little bit the spring, the other end doesn't work. So I'll draw the analogy. If you have a lever, you can move this and generate very small movements here. Say this is holding a big load. You can move this and make very small movements here, even if there is friction. But if you are activating this lever through a spring, it's different. You can move this and the spring may just change and nothing will move. So the problem is that when you step big steps, you're generating big delta thetas and you generate big delta torques, which overcome the friction and stiction and everything. But if you start microstepping, you generate smaller and smaller delta theta, so you make smaller and smaller changes in output torque, which are not enough to move the load. So the question is, so what's the end of the story? So how accurate is a stepper? So I'll give you some data. The stepper itself, by its data sheet, it says that accuracy of a stepper, the better ones are 2% of step, and the poorer ones are 5% of step. That's a nominal accuracy. Okay? Okay. So this is actually not bad, because one step is only 1.8 degrees. So 2% of 1.8 degrees, so that is 2% times 1.8 degrees. Okay? So that's 0.036 degrees, because it's the same as 1.8 divided by 50, right? So that 1.8 divided by 50 is 0.006. Okay? That's actually not bad. So if you look at a stepper, you say that a stepper only costs $10, $20. It's actually accurate to much better than a tenth of a degree. Even this would be 5% of 1.8 degree. Okay? So it'll be like 1.8 degree divided by 20, it will be 0.09, which is also not bad. So let's say a tenth of a degree or better. Yes?
Are these specs up for no load?
Pardon?
Are these specs up for no load, is that correct?
Yes. But here it will actually not deviate much from that, because that theta and that power angle, that is for one step. So this whole range, theta goes from 0 to 1.8 degree, and about halfway through it already reaches maximum. So basically, if I change it here, okay, I'll get big changes in torque, because that whole power angle inside the motor, it doesn't look like this. There are 50 of those. So this whole graph and this whole calculation applies to a segment which is only 1.8 degrees, and within that segment you have the power angle. So actually here it is pretty good, because even with some load it still be maybe twice this error. So a stepper motor as is actually not bad at all. You can easily expect a tenth of a degree is a safe assumption even with load. By the way, why is it so accurate? It sounds surprising, because a tenth of a degree is 1 part in 3600. That sounds pretty good for such a cheap small motor. So can somebody based on what we discussed many times before in sensors and so on, what gives such a cheap, simple stepper motor an accuracy which is, this is 1 part in 10,000, right? 2% is 1 part in 50, and if it has 200 steps, this gives me 1 part in 10,000. So a little cheap motor like this actually has absolute accuracy of 1 part in 10,000, which is very good. So what's the trick? What's the secret ingredient which makes it so accurate?
Because there's 50 full pairs it's averaging this.
Ah, beautiful. How come only you knew? How come only you said that? Because all of you should have jumped up and said averaging. Because I gave you many examples that the secret to high accuracy is averaging. I gave you the example with the encoder. You can average the whole disk. Remember? So I gave you the example of the indexing, which can index by gears to arc seconds. So whenever you have a lot of averaging, things get accurate. Now, because this is 50 poles, all the imperfections of the coils and the armature get averaged. And that's what makes a stepper so accurate. Good. But, strangely enough, the microstepping doesn't improve the accuracy. It just improves resolution. And it makes sense, because the microstepping just follows these steps and interpolates between steps. So if you have a stepper and it's step to position like this, the microstepping just interpolates with smaller steps. But if this step has an absolute error of this, microstepper cannot fix it. It just can give you fine interpolation. Is that clear? So keep these numbers in mind. At the best, in absolute, a stepper motor is 1 part in 10,000. And if you calculate it in degrees, it's better than 1/10 of a degree, including load and everything. Okay? And keep this in mind, that in order to run a stepper, you have to ramp it up and then ramp it down. Otherwise, you lose most of the performance. Good. Okay. So what do people do if they want a rotating field motor which has a high starting torque? Because I explained everything about these motors is great except starting characteristics. So if you want a rotating field motor with very good starting characteristics, what do you do? Pardon? It still doesn't help the starting, because it still has a fundamental weakness. When it has a high inertia load, it doesn't want to start, it vibrates. Yes?
Couple it with another motor.
One way, and actually ties into the next subject. You can make a motor like that when you start it, it behaves differently, like a different type of motor, and then switches to synchronous. So that different type of motor, which has good starting characteristics, that's called an induction motor. And that was actually the motor Tesla invented. I told you the story about Tesla, that the professor made fun on him because he said, how do you get rid of the sparks? So the motor he conceived is actually the induction motor. He conceived the rotating field idea, but he wanted to build a motor, and he tried different ideas, but the motor which worked best and the motor which he invented is the induction motor. So that's what we are going to talk about next. Okay, so for that maybe I'll turn on the projector and I'll give you the same demo I gave you the rotating field. You start slowly with a ramp, just exactly like a stepper. You can't start it at full speed unless the speed is very slow. But today it's easy. Today you have electronic drives like these variable frequency drives that you can do that. In the old days it was complicated because you didn't have electronics. So today it's much less of a problem because you just use this PWM generated, this thing, PWM generated VFD, and you can start it as gently as you want. But the motors at home, like if you look inside your washing machine, inside your table saw, inside your house furnace, they were designed at times before electronics, and also to cut costs, to keep costs down. They didn't want to do it this way. They were looking for a cheaper way. Okay, so I'm driving it with 3 synthesized phases. Now you understand much better how I synthesize the 3 phases. It's just PWM, and because it's a crude PWM, remember this was a jerky motion, but it doesn't matter. Okay, and when I start it, you'll see the 3 phases oscillating 120 degrees out of phase, but the rotating field rotating. Okay, that's what you've seen before. Okay, now if I stop it and I put inside, instead of a magnet, I put inside a contraption which looks like this. I take a piece of metal and wind a coil on it, and I short the coil together. So it's basically back to the same motor. Let's draw it with the 3 poles like we had before. So it has a 3-pole motor, 3 coils, rotating field, but instead of a magnet, I put in a piece of steel which has a coil on it, but the ends of the coil are shorted together. Okay? So it took quite a leap of faith from Tesla to come up with that. So what will happen? So first of all, the field will rotate. So inside this, there will be a reversing field, right? The vector goes this way, then it goes reverse. So the magnetic field inside this core will switch. So what will happen?
Current generated in the coil.
Yes, because if the magnetic field is flipping, there is a current generated in the coil. And at the beginning, at startup, when this rotates at full speed, the current generated will be very high. Because the difference, this is stationary. Let's say if I plug into the power line, this will rotate at 60 Hertz at the power line. This will be stationary at the beginning, so there will be a 60 Hertz, this will see 60 Hertz magnetic field, just like a transformer. So this will be just like a transformer with a short on it. So there's a huge current created. Now this huge current creates a huge magnetic field. And that huge magnetic field will lock into the rotating magnetic field. Because if you have 2 magnetic fields, there is a force between them. Okay, and they lock together. One will pull the other. But the moment this will lock into this field, what will happen then? So let's say a huge current was induced, so this starts being pulled by the magnetic field. Remember, if I didn't have a coil, if I just put a piece of steel, it will also be pulled by the magnetic field like a synchronous motor. But just a piece of steel will be pulled not so strongly by just by the magnetic field. But if I put a coil on it and the coil is shorted, the current will be huge because it's a short, so the magnetic field will be much bigger than just a piece of steel. So now it will be very strongly pulled. But what happens if it really follows the magnetic field? Yes?
The magnetic field won't be changing anymore. So
True, very good, very good. So then what will happen?
the current will stop.
Pardon?
There won't be any more current.
And then what happens? Okay, so first, I'm not sure everybody listened. If this really is synchronous with the magnetic field, it doesn't see any more change. If there's no change, there's no current, there is no field. There is a little bit of just drag on the steel. But you can actually do it without the steel. To make it even simpler, imagine you just had the coil with no steel. So now if there is no steel, there is no magnetic pull at all. Maybe it's better to explain it this way. Let's just start just with a coil. So if you just start with a coil, there is no magnetic pull at all unless there is current. So at the beginning there is a huge current, okay? Now, but if it locks in, there is no current because it sees constant field. So what happens then? There's no current, there's no torque. So what happens then? It slows down. It slows down till when? So it has to find a point where there is enough current flowing to keep it going, but it always has to slip. If this field rotates at 60 Hertz, this can never reach 60 Hertz because then there will be no current. But on the other hand, it cannot be zero because then there is a huge current. So it has to find some frequency which is a bit below 60 Hertz, so the difference induces enough current to generate the torque desired. But if you load it, this slows down. The moment it slows down, there is more current generated because the difference is bigger. So it has a very nice characteristic. Not quite like the series wound DC motor, but it has a nice characteristic that if you try to slow it down, the torque will go up. Okay? Now, the reason we add the steel is simply to increase the fields, because as you know, the killer in all these schemes is the air gap. You don't want a big air gap. So the only reason you add the steel is that the magnetic field has less of an air gap to go through and you get bigger magnetic fields, just like a transformer. But it's not the steel which is being dragged by the rotating field. The main force here is a huge current which causes a magnetic field. The reason there is steel inside is just to close the air gaps so the transformer action is more efficient. Okay? So what I have here is I have a piece of steel, and this is made to look more like the actual rotor of an induction motor. So what I have is I have a piece of steel which looks like this. It has slots. Okay? And that's how a real induction motor is made. And in the slots, you put a single turn which is shorting. So you don't have to have one coil. You can have several coils. And each coil is just a single turn which is a short circuit. Just like this last week when I showed you this copper ring. And the way it's done, you have two copper discs and you have copper pins going through it. So it's all shorted. The steel is surrounded by copper. Okay? So this is equivalent of this. Now it turns out it doesn't matter if there is one turn or 1,000 turns, it works the same. Because if it's one turn, there is a much lower voltage, but also a much lower resistance. So the current will be the same. Because the current is Ni. So if you have many turns, the single current will be low times a big N. But if you make one big short circuit turns, the current will be very high and N will be 1. But the effect is the same. So it's easier to make one turn because it's shorted anyway. Okay, so now we put this inside here. Put it inside the magnetic field. Okay. And it has a green dot, so you can see if it rotates or not. And we turn on the magnetic field. And what you see, it rotates. Again, a jerky motion because the PWM is crude. And it seems to be doing the same as the magnet before. Okay, but if you hold the magnet above it, you see that actually they are not synchronous. Now you watch both the magnet and the green dot. And you can see that the magnet is moving faster. Watch the green dot again. It's hard to do it in a way you can see the dot. Now you can see the dot. You can see the magnetic needle is going much faster. Here it appears to go twice as fast as the green dot is going. Is that clear to everybody? Okay, so it's clear to everybody why the green dot can never catch up with the magnetic field. Right? If it catches up, there is no induced frequency, no induced current. So that's called an induction motor. Okay? Now, if I slow it down, well, this has a very near zero torque. But if I slow it down, it will still keep going. It just goes slower with more torque. Okay, so that's what you have to thank Tesla for. Okay. Now, what I want to do is I'll pass it along. Okay, because I want people to look. Okay, projector off. Good. System off. So, I want people to have a look at this, which you have seen before, but I want to have you to have a look at the construction of the armature. Okay, so now, so if we try to make a plot, again, omega versus torque for an induction motor, so this is omega, this is torque. I also want to remind you that in some books the coordinates are reversed. If you look in books, many books show torque on this axis, so don't be confused. Okay, so we already remember that a synchronous motor will look like this. Stepper motor will look the same because it's a synchronous motor. So how will an induction motor look? Okay, so let's call this omega synchronous. Omega S meaning the input frequency, the synchronous frequency. Okay, in this case, if it's a power line, this will be 60 Hertz here. Okay, so the induction motor, even at zero torque, cannot start at 60 Hertz, because if it started at 60 Hertz, there will be no induced voltage inside. Okay, so it will start a little bit less than this. Okay, like this. Now, when torque, okay, when the torque goes up, the motor has to slow down, because it has to slow down. Actually, it starts pretty close to it, but I'm just exaggerating this. Okay? Now, when torque goes up, omega has to go down. In other words, the armature speed has to go down to generate a bigger delta F. Okay, if you think about it, this is the momentary omega, and the delta F, which induces the current in the armature, is actually delta omega is simply omega S minus omega, because that is 60 Hertz and this is, say, 55 Hertz, which is the speed of the armature. So the difference is 5 Hertz, and that's what runs the transformer action, which induces current. Is that clear? Good. So it goes up to here. Okay, here, now at some point it can't do it anymore, because at some point even if you stall it and create a huge current in the armature, there is still only so much magnetic field in the stator, and same as in a DC motor, it can overpower the magnetic field of the stator, and basically it can't work anymore. So at point it goes like this. Now what's interesting here is that it actually has this kind of a behavior. Again, that it likes to run. I think this is highly exaggerated, because this point is actually typically up to here. So if I draw it to scale, this is exaggerated. To scale, it looks like this. To scale, if this is omega synchronous, it actually looks like this. Okay? So it's running very close to synchronous frequency, and then the torque peaks. Okay, now if you start loading it down more, it just starts to break lock. It doesn't work so well. Okay? Now, so it's basically the operating range of this motor is only this part. Because if you load it too much, the induced current becomes too much, it overpowers the current of the stator, you start losing torque, and the thing becomes unstable, just like a synchronous motor. Okay? So as I said, in some books, it's drawn the other axis, torque versus omega, and in case of this motor, sometimes it makes more sense. It goes like this, okay, and then it collapses. So this, of course, here, this is synchronous speed, omega synchronous, and this is a working point. And typically, when you go at home and you look on your tables or washing machine or furnace, typically if it's a two-pole motor, okay, which is supposed to be 3600 RPM, it will say on the label 3550. So it's almost synchronous speed. If it's a four-pole motor, okay, if it says, it should have been 1800, it says 1750 or 1725 sometimes. Here it may say 3500. It depends on the motor. But typically, the delta F, if I look at this graph, this is a delta omega to the working point. That's the working point. The delta omega is a few percent, that's all. Okay? Say if I look at, say if the synchronous was 1800, okay, and I run it at 1725, okay, that's just about 5% difference. So it's very, very little difference. It runs almost, if you draw it to scale, this point is at 95%. Okay? Another way of saying it, the frequency the armature is seeing is only a few hertz, 2-3 hertz, because it's 5% of 60 hertz, right? It's only 5% of 60 hertz, only 3 hertz. So the actual, it almost catches up with the synchronous speed. But it can never catch up, because if it caught up with the synchronous speed, the torque will be 0. Because here, if this really caught up, there will be 0 torque. So remember, this is a highly exaggerated curve. The real curve looks more like this. It's almost at synchronous speed, and the working point is here. Okay? Good. So this is the most common motor in the world, actually. All industry runs on this motor. It's not constant speed, but it has beautiful starting characteristics. Okay? So because of that, that is the most common motor on Earth. Okay? Remember, if you want to look at the starting characteristics, it's easiest to see it when you draw it reverse. When omega is 0, it has this torque. The torque actually goes up. Now, this is a bit funny. You would think that the motor will look like this. You would think that if you stall the armature, you get the biggest torque because you get the biggest delta F. And when it reaches synchronous frequency or near synchronous, it still have reasonable torque. But so you would actually think it will look like this, but actually it looks like this. So the answer is, surprisingly, these motors are optimized for this frequency. So if you just build a motor without any optimization, it will actually look like this. Okay, or in this curve, in this curve will look like this. Okay, but since you know the motor will run all its life at this speed, you are trying to optimize the copper and iron and winding not to the starting conditions. You're trying to optimize it for the running conditions. And when you optimize it for the running conditions, this thing suffers. The starting torque suffers. So that's the reason why these motors have a funny curve like this, because all what matters is where they'll spend all their life running. And they have enough torque to start. Okay? The starting torque is anywhere from 50 to 80% of the running torque. But the whole optimization is around this point. Say, this is the most common motor. All the stuff at home is running on this motor. Like your washer has this motor, your furnace has this motor. So everything in your home, which has a big motor, run at 1725. So the whole motor is optimized around this point, and it spends all its life running at this speed. Your fridge has this motor inside. The reason you have this motor and not this motor, because this motor runs a bit too fast for most appliances, and it's noisy. Because at home you want the motor to be quiet. So if you have a washing machine, a furnace, all these machines, you don't want the motor to be noisy, so you prefer this over this. That's the only reason. Because you can gear this down. It's the same size motor, you can gear it down with a pulley or belt. But it's still, you hear the noise of the faster motor. So you only have this motor in your table saw, which you need the blade to go fast, or on the grinder, right? Anything except table saw or grinder at home has this motor. Good. Okay. And again, this one doesn't need to ramp. This motor is a bit like a DC motor. You can start it at any frequency. It will start here and pull up to the working point. You don't need to ramp it. You don't need to do anything. Okay? That's another reason why it's so popular, because in big industrial motors, this VFD can become expensive. If you have a 100 horsepower motor, that VFD can cost more than the motor, because you're dealing with hundreds of amps. But in this motor you don't need anything. You start it and it will find it, it will pull up and lock, not lock, but stabilize at this design speed where the motor is optimized for. If you take the load off, it will go a bit faster. It will climb up to 1780, 1790. Just like this graph shows, if you take the load off, it will try to climb to synchronous speed. So it's still not bad speed control, because no load to full load, it's only a change from this to this. So it's still pretty constant speed. At least for industrial things, it's good enough. Okay. Any questions about the induction motor? Okay, so now let's go back to this demo, which I gave you a challenge last week that anybody who will explain this doesn't have to do the final exam and gets an A for the course. Okay? But nobody came up with an answer, so I'll tell you the answer. So the demo I gave you, that when I turn on this motor, it didn't want to rotate. Say if I stall it, it didn't want to rotate. No, now I turn it. But if I start it, let's say I stop it, it doesn't want to rotate. But if I start it one way, it will rotate with full torque, with good torque. If I start it the other way, it will go the other way with full torque. But on its own, it has no torque. It just sits there and hums. Okay? So now you are one step closer to understand the mystery. Okay? So, okay. So what's the explanation? So this is an induction motor. So this is actually an induction motor, not a synchronous motor. You can look inside, and if you look inside, you see the armature. It looks exactly the same as the one I passed, but it's aluminum instead of copper. Because aluminum is cheaper than copper, so I mentioned that these armatures are a shape like this, which is all cast in a conductor to make a short. So typically it's cast in aluminum, not in copper. So this part is steel, and this part is aluminum to short everything out. Okay? This type of rotor is called a squirrel cage rotor. You may have seen this term, squirrel cage rotor. Squirrel, double R, right? I'm getting confused. How do you spell squirrel? Is double R or single R? Double, yeah, squirrel. I'm getting confused. Yeah, squirrel cage rotor. Okay, good. So that's what's the name. I don't know why. Maybe because it looks like these cages that squirrels climb on them. You know, the thing that's the toy for squirrels to climb on. Because physically, when you look at the thing, it actually looks like this. It actually has these bars. The bars are a little bit slanted for the reasons I explained before. It looks like the toy squirrels climb on, right? So that's called that's a cross section, and that's a view. So this standard squirrel cage motor, okay, and it has aluminum instead of copper. So now we're getting to the mystery. Why can't it start on a single phase, and why, if I start it, it works great? Okay, so it can't start for a very simple reason. On a single phase, there is no rotating field. So you know that. So this motor inside is actually a two-phase motor. It has one coil like this and one coil like this. I showed you before that when I put a capacitor in series, I am generating the second phase, everything is good. But if I only could power up one phase, obviously I don't have a rotating vector, I just have an oscillating vector, so it cannot start. But why, when I start it, it seems to be running fine, although this other coil is not connected. When I start it by hand, it still has only one coil, it still has only one oscillating vector, but it works fine. Okay? But now you don't get an exam from the exam, because I already started explaining it. Yeah, okay?
The inertia is carrying through to the oscillating vector in that case.
But why? How would the inertia is a mechanical property, how would it affect the rotating vector, rotating field? The rotating field is a magnetic problem. So why would the inertia affect the magnetic field?
you have the induced current in the rotor, and you're causing just a brief gap between them, and then that carries through somehow. Like you have two magnetic vectors now that are.
Why do you? You're getting very close. Okay, so. Okay, so the most. Anyways, this is not a simple question to explain, and there are several ways to explain it, and I'll give you the most elegant one, but I want to hear how close you come. So anyway, you came close. Yes?
The rotating inductor induces a current in the other stationary inductor at a phase difference from the.
Close, but okay. So anyway, the most elegant explanation is this: when you have an oscillating vector which oscillates up and down like sine omega t, you can always represent it, just for the proof, you can represent it by two counter-rotating vectors. So when you have a vector rotating this way and a vector rotating this way at the same speed, the resultant is always a straight line. Because of symmetry, it will always stay in the center. So at this point, when the two counter-rotating vectors are here, it will be 0. When the two counter-rotating vectors are here, it will be negative. So any oscillating vector can be represented, just for analysis, by two counter-rotating vectors which rotate exactly at the same speed. Is that clear to everybody? Good. Now we are talking about an induction motor. So now we have a single coil. It has a single oscillating vector, but next to it we have an armature which looks like basically a shorted coil. So here we have a coil which is shorted. Right now it's standing here. This generates an oscillating vector. This coil doesn't rotate. But if we view the oscillating vector as two counter-rotating vectors, and this is a linear system. In a linear system you can apply linear superposition. So you can say the torque on this is going to be the sum of the torque created by this vector plus the torque created by the other vector. Because so far it's a linear system. Okay? But now, so normally if it's standing still, these two are the same, the torque will be 0. But the moment I start rotating this, so let's say this is omega synchronous and this is omega, because I started rotating it. The moment I started rotating it, these two torques are no longer the same. Because if I rotate it in one direction, it reduces the frequency difference with this vector, and in the other direction it increases it. Because I have two rotating vectors like this, but I have a rotating armature next to them. So if I rotated the armature this way, in the direction of this vector, the delta frequency is this minus this, because they're going in the same direction. But if I compare it to this vector, it's going to be this plus this, because they're rotating in opposite directions. So this torque is proportional to omega s, say in this case minus omega, and this torque is proportional to omega s plus omega. Okay? So now I created two torques which don't cancel out. And it's a huge difference, because if I give it a good spin, let's say if I manage to spin it up to 60 hertz, this torque will be 0, this torque will be driven by 120 hertz. Okay, so it doubles the difference. So the moment it's stationary, the torques are the same, it cannot start. But the moment I spin it, as soon as I started spinning, there is a differential torque, and then it keeps revving up and locks in to near synchronous speed. So is that clear? Okay? Because I think that is the most elegant explanation why these motors, once they started, generate their own torque, although they are still running on a single phase, which can only generate an oscillating field, not a rotating field. So because of that, some motors take advantage of it, So when you look in your house at induction motors, there are two types. Inside, if you look inside your house induction motors, they all have this hump, because this hump is a capacitor to generate the second phase, as we discussed a week ago. But when you listen to this motor start, some of them they start just like this one and keep going, and some of them start and after 1 second you hear a click. Typically on your table saw, it will start, and if you listen after 1 second you hear a click. And what that click is, it's a centrifugal switch inside which disconnects the capacitor. Because once it started, it doesn't need the capacitor to generate torque. Okay? And there is some advantages then on running it without a capacitor. It's a bit more efficient. So this is called, with the one with the switch, are called a capacitor start induction motor. They don't need a capacitor to run, they just need a capacitor to start. A centrifugal switch is very simple. You have some weight on the armature, on the rotor, on the shaft. You have some weight with a spring, and the switch is actually stationary. So when it runs fast enough, that weight opens up and pushes the switch. You don't need the switch rotating, right? You just need the weight rotating. Okay? Clear to everybody? Okay, speed up passing the, oh, you passed the motor to everybody. Good, that's good. Very good. Okay, so any question on induction motors? Yes, please.
Said induction motors were used in electric vehicles?
Okay, yeah, so for example, if you look at most electric vehicles, the old ones, we use the DC motor for obvious reasons. People may not know that, but electric vehicles are 100 years old, and at times in history they were very popular. For example, today everybody is talking about charging stations for electric vehicles. In 1905, New York was full of charging stations for electric vehicles, and there was an electric car called Baker Electric, which was very popular. You can actually see an episode on it in Jay Leno's Garage, which has an episode on the Baker Electric car. They show a Baker Electric, so there were charging stations everywhere. It was very popular. But then the gasoline engine did much better because it produced a lot more power, and the electric cars died. And now they're coming back. So the old electric cars, or the golf carts, or the forklifts, they all use DC motors. Compound wound, mixed, series, and parallel. The new electric cars, like the Tesla, the Renault Leaf, they all use induction motors. Now, one advantage for an electric car, because of the variable frequency drives, that you can make an induction motor run at a very high speed, and you can gear it down. So remember that power is torque times omega. So if you want a very small motor, you can give it a very high omega, and you'll have a huge power from a small motor. So a Tesla induction motor, which is about 250 horsepower, is this size. I think of it, it has the same power as a V8, like a big American car engine, and it's this size, the whole thing. You can lift it easily. It's about this diameter, this long, because it runs at 18,000 or 20,000 RPM continuously. Okay? That's why it generates so much power.
And you just use a transmission to change speed, or?
Yes, fixed transmission. Fixed, no gearbox, just fixed ratio. The original Tesla uses a 2-speed gearbox, and then they did better control, and they used just a fixed ratio, like a 10-to-1 gear or whatever. No switchable gears. It's a big advantage.
Okay. And then just to control the speed, you're just controlling the drive.
As a VFD, the whole thing, which when you step on the gas in the Tesla, you're actually stepping on the pot on this. It has exactly this thing inside, and has a potentiometer, and you're stepping on the potentiometer. That's the gas. Okay? That's simple as that. And it's very good. I actually drove a Tesla. It's amazing. Because it has very good starting torque. It has, even the Tesla S, which is a passenger car, not a sports car, has a sports car acceleration. Because, now, something to point out, if you have a gas engine, the gas engine has a certain displacement which can produce a certain torque. You cannot exceed this torque even for 1 second, because it's the same as a steam engine. There is some pressure, makes a force. You cannot for 1 moment get more power out of it. The power is fixed. Now an electric engine, electric motor is very different. You can get as much power as you want out of it for a very short time, because it's the same as an actuator. There is a steady state limit and there is a demagnetization or other limits, but for a very short time you are not limited by the steady state limit. So an electric car will always out-accelerate a normal car if you want to, because for 1 second you can draw hundreds of horsepower from this little engine, and then you have to stop because it will overheat. And that's what makes electric cars interesting for people who like cars, that you can make a car which actually has phenomenal performance for a short time. Okay, continue next week.